Okay, welcome to the video for today. Today what we're going to be covering, and starting at least, is Unit 15, which is an HL topic. So if you're an SL, you don't need to watch this video particularly unless you want to just go a little bit above and beyond. So today we're just going to start off. We're going to do a little bit of a series of videos and break it down. Break it down a little bit into some shorter videos. So first, what we're going to do is we're going to kind of cover, this unit 15.1 covers like energy cycles. So what that means, we'll be doing the Born-Haber cycle. And this is kind of a very similar thing, right? We talked about in the last video. There are delta H values, right? They are state functions. So they're state functions, which means that, however we get to the final product, if we imagined, sodium metal reacting with chlorine gas, reacts to form sodium chloride, there can be different ways to do this, right? We can either go straight forward this right way and react sodium with chlorine, or we can go through another way, right? We can turn sodium into a gas. We can then ionize the gas. That's our ionization energy. So we can turn it into sodium ions. Same thing with chlorine. We have chlorine in the gas phase. We can break up the chlorine-chlorine bond to form two chlorine atoms. This one we've let go of two electrons, so we can say what's the electron affinity of chlorine, so that we can get sodium positive plus chlorine negative, and then from there, right there in gas phase, we need to start working through the lattice enthalpy. So the lattice enthalpy, which is something that we're going to introduce today, it's how much energy we require to break up a solid ionic compound into its constituent ions in the gas phase. So we can come back down and we just do delta H of lattice enthalpy, and we could arrive at the same product. We arrive at it a few different ways. So using this information, we can solve we can solve the delta H of formation. We can solve how much energy is gained and how much energy is released in this reaction, do the difference, and then calculate the delta HF. Because some reactions, why we want to do that, right? This reaction occurs like this. We can react chlorine gas with sodium metal and form sodium chloride. That's a reaction that can occur. But if you imagine something like carbon reacting with hydrogen to form benzene, C6H6, right? This reaction does not occur in this way. We can't just take wood outside, react it with hydrogen, and magically form a benzene ring, right? There's different reactions that must occur in order to end at that final product. So that's why we can't calculate the delta HF directly, because these reactions are not always straightforward. But in this case, benzene might not have been the best example, because what we're dealing with, at least in IB chemistry, we're dealing with only ionic compounds. So only ionic compounds for us. And of course, C6H6, that's a covalent compound. So we can't really use that example too much, but that's just the description for why we can't directly do delta HF. So okay, so what we're going to be discussing in this video, first we're going to just be discussing different parts of the Born-Haber cycle. So that's exactly what we're doing here, right? Arriving at the final product and calculating delta HF, because sometimes we can't calculate this directly. So we're going to use a bunch of different delta H values in order to calculate that. But we need to know, what are these delta H values? What is going on? What do we call it when we turn sodium from a solid to sodium to a gas? And we need to go over these names. So okay, let's start with the names. So we've got the lattice enthalpy, which is going to be our first one. is the change in enthalpy from 1 mole of a solid ionic compound into its constituent gaseous ions under standard conditions. So our lattice enthalpy, our first one, delta H lattice. So this is breaking up, we can say it a different way, breaking up a solid ionic compound into its constituent gaseous ions. So an example of that would be right here, right? We got that already. We've got sodium chloride, solid, and we break it up to form sodium ions in the gas phase plus chlorine ions in the gas phase. So it's how much energy we have to input. So we have to input energy in order to, of course, we got to take a solid and turn it into a gas. That's an endothermic process. And we also need to break the ionic bond. We need to break the attraction between the sodium and the chlorine ions. So it's an we have to input energy in order for this to go forward. Okay, so let's look at the second one that we have to cover today. Electron affinity. So this is something that we covered, I believe it was in Unit 2. And it's basically the change in enthalpy when 1 mole of a gaseous atom attracts 1 mole of electrons. So with that would be something like right here. Right, we take chlorine atoms, chlorine, because you can see right here, atoms. So we've got chlorine atoms, and it attracts an electron to form a chlorine ion. And this will be, let's say 2, and this will delta H electron affinity. So electron affinity. And this delta H value, this delta H, let's say delta H magnitude, it depends on the element that we're looking at. The magnitude depends on the element, right? We've got chlorine atoms right here, and we know chlorine atoms are very electronegative. So they really want it. So its delta H value will be different than if you imagined, right? We had let's say calcium metal, right? Calcium metal. We could add an electron to that to form calcium minus ions, but we know that metals don't like absorbing electrons. So this would be a lot more. We have to put in energy to make it absorb an electron, and it would be very happy, and it would be ready to give that electron away as quickly as it can. So right, non-metals are better at absorbing, taking in electrons, and we'll see that with our values for delta H, how the magnitude of them. So let's look at number 3, the third one that we have to know. And then we're going to practice solving a few of these. So the third one that we have to know, enthalpy change of atomization, delta H of the atom. And remember this 0 in the top right-hand corner means in standard state, 1 atmosphere of pressure, 25 degrees Celsius. Is the heat change when 1 mole of the gaseous atom are formed from the element in its standard state. So gaseous atoms. So if we look at elements in their standard state, we can look at sodium. I'll give you an example. We'll write down the definition first. So delta H of atomization. What that is that I'll write down 1 mole of gaseous atoms, right? Atoms, let me change that color because that's the most important part. 1 mole of gaseous atoms formed from elements in their standard states. So, right, this depends on the element. Right, we can say sodium solid goes to sodium gas. Okay, that's fine. We've just basically boiled it and turned it into a gas. But this is not the same thing for chlorine, right? Chlorine is diatomic. So we need to change that to atoms from elements in their standard states. So we need to change this to atoms, so it's 2Cl. Because, right, its standard state is in the gas phase, and we're not changing it from a solid to a gas, we're just changing it from a gas into its atom. So, right, atom is non-bonded, it's by itself. Okay, let's look at the next one. Bond enthalpy. So this is something that we've covered in the last unit, right? Bond enthalpy is the energy needed to break 1 mole of the bonds of the gaseous molecule. So we can say 4 delta H of bond enthalpy. So that's the energy required to break a covalent bond, and that's in gas phase. I'll make sure I got it. 1 mole of gaseous molecules under standard conditions, so delta H naught. Energy required to break 1 mole of bonds in the gaseous molecule. 1 mole of bonds in a covalent bonds in gas phase. So right, that'll have to do with this delta H of atomization too. So we've also got, this can be represented as our bond enthalpy, but also as atomization. But this one, right, this can't be represented. Sodium cannot be represented as bond enthalpy because there was no bonds to break when we changed it from its standard state into the gas phase. Okay, let's look at the ionization energy. Remember, this was our tricky one that we did in Unit 2. It's gaseous atoms again. So delta H, let's say 5 delta H of ionization energy. And this was basically the energy required to knock off 1 mole of electrons from an atom in its gaseous state. So, the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of cations. So what that one would be is we'd take our chlorine atoms that we have already from an atom in its gaseous state, and what we're doing, we can do this with chlorine, right? We can knock an electron off, form a chlorine cation and an electron. Or we can do that with sodium in its gas phase. We input some fast-moving electrons to bombard this, and we knock off electrons. So we get sodium positive in the gas phase, plus electrons. We've knocked off an electron. So the energy required to knock off 1 mole of electrons from 1 mole of atoms in their gaseous state. And that might be the last one. Let's see. Okay, so this is just how to represent them. So delta H of atomization, right? If we go back to our other sheet, delta H of atomization, right up here at the top, breaking up a solid ionic compound into its constituent gaseous ions. Oh, that's the last thing. Sorry, atomization. There we go. 1 mole of gaseous atoms formed from elements in their standard states. So if we had a solid in the standard state, we change it into the gas phase. A second one, bond enthalpy, was just the energy of a covalent bond. Ionization energy, the energy required to take a gas, knock off an electron. We had electron affinity, the energy released when an atom in its gaseous state absorbs an electron, and lattice enthalpy, a solid ionic compound into its constituent ions in the gas phase. And now we've got the last one, which is solubility, delta H of solution. So it's basically how much energy you gain or lose when you dissolve an ionic compound. Dissolve 1 mole of an ionic compound. So if you dissolved 1 mole of salt, will the solution gain or lose energy? And we've got the delta H of hydration. So these are 2 more we can do. So the delta H of solvation. Let me go back. We'll do number 6 right down here. Delta H of solvation. And this is energy, energy gained or released, when, let's say when 1 mole of solid ionic compound dissolves in solution. When 1 mole of solid ionic compound dissolves in solution. And the example is right here. We just take any solid ionic compound, sodium chloride, solid, and we break it up into sodium aqueous and chlorine aqueous. So it's just the energy required to break up this ionic bond. But then we've also got 1 more, delta H of hydration. And that'll be energy gained or released. Energy gained or released when an ion is hydrated in solution. So an example of that would be, right, you have a sodium ion, and like we know, water is polar. So water is polar. We've got a delta negative here and delta positives here. And basically what occurs is that this water solvates or hydrates the sodium. So this negative charge will come over closer towards the sodium to hydrate it, to solvate it. So basically OH, because the delta positive will repel from the sodium and the delta negative will attract to the sodium. So that'll be some of our delta H of hydration. And that's all we're going to do for this video. Next video, we're going to construct some Born-Haber cycles. I'll see you then.